Okay, here we go. Let's first review the basic trig functions. They're your parent functions. They're the functions you're going to be stretching and compressing, etc., etc., okay? Translating left and right, up and down. Okay, for y equals sine x and y equals cos x, we focus on 5 key points, a maximum, a minimum, and 3 intercepts with the x-axis. For y equals tan x, we focus on 3 key points and 2 asymptotes, okay? Because sometimes tan x is undefined. Graph y equals sine x using key points. Note the period is 2 pi. So in other words, that length of one cycle, which basically looks like that distance on the parent function is 2 pi radians, or 360 degrees. Special points occur every pi by 2, right? Every pi by 2, you either have a mix, an intercept, a min, an intercept. It kind of alternates like that. But just for your information, special points occur every period, whatever the period may be, divided by 4. In our case, the parent function has a period of 2 pi, so that's 2 pi divided by 4 is pi by 2, right? So these key points, the min, the max, and the intercepts occur every pi by 2, right? And if you recall, the max equals 1, right? That's why if you go inverse sine of 1.5, you'll get an error message, because you can only go up to an inverse sine of 1, right? Your min is minus 1. Domain, we'll just write that here, is x such that x is an element of real numbers. Range is y such that negative 1 is less than or equal to y is less than or equal to 1. Y is the element of real numbers. Okay, so here's our y-axis, here's our x-axis. So the maximum is 1, so we'll draw it up to 1. The minimum is minus 1, and now we're all set to go. Sine of 0 is 0. Sine of pi by 2 is 1. Sine of pi is 0. Sine of 3 pi by 2 is minus 1. Sine of 2 pi is 0. So there you go. There you have, that's your parent function. That's what you have to remember. Notice your max, your min, and your 3 intercepts. 1, 2, 3. Okay? Each cycle has a max, a min, and these 3 intercepts. That's on the parent function. Now, we could continue that because it is periodic. It means it's repetitious, right? So this is 4 pi. At 5 pi by 2, it would go back up to 1, right? 6 pi by 2 is 3 pi. It go back to 0. This would be 7 pi by 2. It would go down to negative 1. And 4 pi, or 8 pi by 2, or 4 pi comes up to 0. So you've got this repeating, it repeats, repeats, and repeats. It can go into the negative as well, because you remember when we did angles in standard position, it went into the negative. So it went to, at negative pi by 2, it's negative 1. At negative pi, it's 0. At negative 3 pi by 2, it goes up to positive 1. See how it's happening every pi by 2? And here at, you can't sit there because the maybe sit over there in Elsa's desk. Okay, because she needs some space there. Okay, are there any questions on y equals sine x? Yes.
When you draw this, you would have to put the arrows, right?
Yeah, yeah, it's okay. I'm not sure. It continues. You could, yes. There's no limit to this, so. Okay, let's look at y equals cosec. Very similar. We have special point. The period is 2 pi, so period divided by 4. You know your special points occur every period divided by 4. Uh-oh, I didn't spell that right. Points occur every pi by 2. Just like in sine, the period is 2 pi, just like in the cosine function. And we'll just do, it has the same domain as sine, x such that x is an element of real numbers. Our range is y such that -1 less than or equal to y less than or equal to 1. Y is an element of real numbers. Okay? So the cosine of 0 is 1. The cosine of pi by 2 is 0. The cosine of pi is -1. Cosine of 3 pi by 2 is 0. And the cosine of 2 pi is 1. So there you have one complete cycle within the 2 pi. Okay? So this can continue just like the sine function. If this is 4 pi by 2, this is 5 pi by 2, plus pi by 2 is 6 pi by 2, which is 3 pi, and this is 7 pi by 2, and this will be 8 pi by 2, which is 4 pi. So again, it continues, then dips up, up. So you got this periodic jumping up and down type of graph. It can also continue in the negative, negative pi by 2, negative pi, negative 3 pi by 2, negative 2 pi. Okay, those are the two easier of the trig functions you have to know. The harder one is, of course, the tan function. Yes. These two? Do you notice it's like, here's sine, right? So can you see, here's the cosine function, right? Can you see it, doesn't it look like the sine? You could write this as an equation of a cosine function. Watch, if I were to write this as y equals cos of x minus, because it's like cos has been shifted to the right, pi by 2. Can you see that I can write this as a, even though I've drawn the sine function here, I could write it as a cosine function with the shift to the right of pi by 2. Right? Cosine, usually the max occurs at 0, 1. Here the max occurs at pi by 2, 1. Can you see there's been a shift of the cosine function to the right? I could write this as a sine function as well. Okay? So we don't need to know that just yet, but if I wanted to write this as a sine function, I would write y equals sine x. Well, sine, it looks like sine has been shifted to the left, so that would be plus pi by 2. Right? It's just like translations. I just have to keep track. Also, we're going to have to make a swap, but I guess it's at 105. I can't find this. Also, at 105, you'll start part 2. Okay, or are you? Sorry? Okay, let's now draw tan. Y equals tan x uses asymptotes and key points. The period is pi. Special points occur every pi by 4 because if you recall, special points occur every period divided by 4. So in our case, the period of tan is pi, so it occurs every pi by 4. Okay? So this is our y, just like it was up here. This is our x, and this is our x. Now, let's just draw it like this. We'll go, the tan function is centered on the y-axis with an asymptote to the right. I'm going to go over 4. 1, 2, 3, 4. So we're going to have an asymptote right there. And then 1, 2, 3, 4, we'll have another asymptote there. This is 1. This is minus 1. Okay, so this right here, x is 0. Remember, special points every pi by 4, so this is pi by 4. This is pi by 2. This is negative pi by 4. This is negative pi by 2. So the tan of pi by 4, the tan of 45 degrees, is equal to 1. Tan of 0 is 0. Tan of negative pi by 4 is negative 1. So now this graph, starting here, goes up like that. As it gets closer and closer to pi by 2, as the graph approaches pi by 2, the y value goes to infinity, and this goes down. So that's your tan function. There's 3 key points with 2 asymptotes. We could do another cycle. 1, 2, 3, 4, 5, 6, 7, 8. I'm just using 8 spaces for one cycle. So 2 pi by 4, this would be 3 pi by 4. 4 pi by 4 is 2 pi. 5 pi by 4, and this is 3 pi, right? So you have one, did I do that? I'm just going to double check. 3 pi by 4. Oh, this should only be pi, right? This is pi, sorry. 4 pi by 4 is pi. 5 pi by 4. And 6 pi by 4 is 3 pi by 2. So here, the period is pi, right? And again, we can just draw that same cycle here, just like this. Tan of pi is 0. Tan of 5 pi by 4 is 1. Tan of 3 pi by 4 is minus 1. So again, you have this. And this just repeats and repeats and repeats. It's periodic. So notice the asymptotes, they occur. The asymptotes are where the graph is not defined. So the asymptotes are x equals pi by 2 plus k pi, where k is the element of integers. Now, because the graph is not defined there, it makes our domain quite complicated. X such that x cannot be any of these asymptotes, right? This is where the asymptotes occur. Pi by 2 plus k pi, where k is the element of integers. I always feel uncomfortable with that, but whatever. X is the element of real numbers. And by Joe, I think we've got it. And our range is, well, y can be anything. Y is the element of real numbers. Yes.
Is it plus k pi? Because it's like
Yes.
every period.
Yeah. Well, do you see how pi by 2 plus 1 pi is 3 pi by 2? So it's every k pi, where k is either negative 3, negative 2.
It's not infinite. That's why.
Sorry?
So you can go on.
Yeah, you can go to positive a million, positive a billion. Yeah. Or you can subtract it, negative a billion, whatever. Whatever. It goes for a long time. It's just very repetitious. Okay, are we good? Those know this. Okay, now let's talk about stretches and compressions and so on and so forth. Did everybody get that? So we have, we're going to do a lot of examples of stretching. Okay. Y equals a f of x. This is just a review. If the absolute value of a is greater than 1, stretch the graph vertically by a factor of a. If the absolute value of a is between 0 and 1, compress the graph vertically by a factor of 1 over a. Remember, we had to do that little correction. That's different from the textbook. If the absolute value of k is greater than 1, you have a horizontal compression by a factor of k. If it's between 0 and 1, you have a horizontal stretch by a factor of 1 over k. Y equals negative f of x, reflect the graph about the x-axis. Reflection about the y-axis is when it's f at negative x. Okay? Here's some review from the previous day's work. Period is the horizontal length of one cycle. A cycle is one complete pattern of a periodic function. A periodic function is a function, well, just for one complete cycle. So for cosine and sine, it would look like that. For tan, it would basically look like that, right? That's one complete cycle. Periodic function is a function that has a pattern of y values that repeat at regular intervals. Amplitude is half the distance between the max and min values of a periodic distance. So amplitude you can calculate with max minus min divided by 2. But to give you the verbal definition, it's half the distance between the maximum and minimum values of a periodic function. Because, you know, the graph of sine, cosine is so complicated, we're going to do stretches, compressions, and all sorts of transformations, not in the same way we did in Unit 3 and Unit 4. What we're going to do is use a technique called fitting the axis to the curve. In other words, we draw a function and we scale it after, okay? So it's a new method of graphing, and it makes graphing trig functions a whole lot easier. Did everybody get everything on that page? So, if you have a sine or a cosine functions, we're going to worry about translations left and right, up and down tomorrow. We're just going to worry about stretches and compressions. And I think we'll do reflections here as well. So notice, for y equals a sine kx and y equals a cos kx, we know the amplitude is a, period is 2 pi over k, right? Where k is that thing, right there. Special points occur every period, which is 2 pi over k, right? Because that k is going to change your period, divided by 4, or every period divided by 4. Tan is a little bit different because tan amplitude is undefined, so A is still vertically stretches or compresses the graph. The period is pi divided by k. You get the k value right from whatever equation they give you. Special points occur every pi over k or divided by 4 or period divided by 4. So let's do an example. I want to show you how beautifully simple this method of graphing is. Not like that tedious way before where we did it in several steps. What is A equal here? 4, right? Note, A is always positive. Note, A is positive, so, sorry, it's not always positive. A is positive, so there is no reflection in the x-axis. And note, there are no vertical or horizontal translations. We are not talking about left and right shift and up and down shift. The amplitude is 4. Okay? And I'll illustrate that on the graph. K equals 6. So our special, so if k equals 6, our period is 2 pi over 6. Our period is pi by 3. So instead of 2 pi, our period is pi by 3. Special points occur every pi by 3 divided by 4. So pi by 3 times the reciprocal, we're dealing with fractions. Our special points occur every pi by 12. So this is the beauty of graphing by fitting the axis to the curve. Give you the next part, okay? And you can use a calculator. Okay, let's do this. Sorry about that. I just had to set a student up there. There's y. Now, we're going to need a x-axis, so just try to draw it in the middle. Okay. So, I think you're going to find this funny for the first time. Note, there is a stretch by a factor of 4. So just count up for 1, 2, 3, 4, right? 1, 2, 3, 4. Special points occur every pi by 12, but let's just mark them off. 1, 2, 3, 4. We need 5 points, right? 1, 2, 3, 4, 5. Has a max, has a min. And you know this is a sine function. There's no reflection. So it's actually going to look like this. It's like we just drew the sine function. Right? So this is 4. The max is 4. The min is minus 4. So this is going to be pi by 12. Now, the next point is 2 pi by 12, which is pi by 6. This is 3 pi by 12, which is pi by 4. And 4 pi by 12 works out to be pi by 3. Finished. Don't you think it's awesome? Pretty simple, right? It's kind of like we drew the sine function and we fit in the scale afterwards. It's called graphing by fitting the fitting the axis to the curve. We fit the axis to our curve. A is negative. Let's look at this guy. A is negative, therefore, oh, before I forget, notice the amplitude is 4. There's our amplitude. There's a 4 there and a 4 there. Amplitude is 4. It's from there to there, yeah?
So every time we graph one of these, do we have to write them in range or only if it asks?
Only when it asks. Okay, A is negative, therefore there is a reflection over the x-axis. So A equals negative 3, but our amplitude is always positive. K equals 1/3, so our period is 2 pi. Because it's cosine, it's 2 pi. If it was tan, it would be pi. Divided by 1/3. Now our period is 2 pi times 3 over 1. Our period is 6 pi. All right, so our special points occur every period divided by 4. So it's going to be 6 pi divided by 4, which is 3 pi by 2. I guess I'll put it there. Okay, so it goes up to 3. I guess we'll put it there. Goes down to negative 3. We need 5 special points. 1, 2, 3. Well, we have 1, 2, 3, 4, 5. Now, cosine, the parent function usually starts there, right? However, we have a reflection, so it's going to start down here. Right? Usually it starts there, but we have a reflection. So now it's going to go up, 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 up. But you're not finished graphing till you write the scale on the axes. Can you see it's been reflected? Because usually cos looks like this, right? It comes down like this. But it's been reflected, right? There's our graph. So it goes up to 3, goes down to minus 3. Special points occur every 3 pi by 2, so this is 3 pi by 2. Add 3 pi by 2 to get the next point. That's 6 pi by 2, which is 3 pi. So 6 pi by 2 plus 3 pi by 2 is 9 pi by 2. 9 pi by 2 plus 3 pi by 2 is 12 pi by 2, so that's 6 pi. Done. Label your axes. So on the test, I expect to see this, 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 this. All these numbers here, I expect you to write them in. Because your graph isn't complete unless you give a complete, unless you're labeling the key points, right? There's 1, 2, 3, 4, 5 key points. 9 pi by 2, yep. No. I just want you to compare to the parent, that's all. But don't do the dotted line. I just showed you that. Now let's do an example of a tangent function. Remember that the tangent function, it has no amplitude, right? Because it goes up forever, we can't take infinity minus a negative infinity and two times infinity and divide it. Just because infinity isn't a number, it's just trying to describe something that's very big. So, but a equals 2, therefore there is a vertical stretch by a factor of 2. K equals 1/2, so therefore we have a period. Normally the period of the parent function is pi, but we go pi divided by 1/2, and that's pi multiplied by the reciprocal. We're dealing with fractions, and that equals 2 pi. Special points occur every 2 pi divided by 4, and that's pi by 2. So once you have those details, can I explain anything better? We're good with this?
Always with period divide pi by the k value.
Yeah. If you want the period for this function, you go, normally like y equals tan x, the period equals pi. So we're doing everything relative to y equals tan x, because that's right. Right? So, yeah, so we take the period pi divided by 1/2. The period of a sine function is 2 pi, so that's why we're going 2 pi divided by 1/3. Okay? Okay, so let's draw this. You draw. There has been no horizontal translation, so you're going to draw it centered around the y-axis. Right? And now we draw the x-axis. Okay, you know you're going to have we'll just go over 4 for one vertical asymptote. And you know, there's been no reflection, there's no negative sign. You know it's going to look like this, but this is going to go up to 2, and this is going to go down. Instead of going up to 1, but we have a vertical stretch. Like normally it goes up to 1, but now we're going to put it up to 2. And it's because there's this vertical stretch by a factor of 2. So now all we have to do is fill in the horizontal scale, right? So special points occur every pi by 2. So this is pi by 2. This is pi. This is negative pi by 2. This is negative pi. It's done. Isn't this better than graphing as a series of transformations? No, as by fitting the axis to the, yeah, I like it too.
So the graph should always look the same, right? Just the numbers are
Yeah,
different,
yeah,
unless
absolutely.
there's translation.
And unless there's a reflection, if there was a reflection, it would be over here. So guys, you want to try the next one by yourself? I'll walk around and see how you're doing.